Greetings, mathophiles. Welcome to a video in which we will explore a way of approaching initial value problems that can be a real time saver, particularly in situations where you have a calculator available for the approximation of definite integrals. You're going to get the most out of this video if you have some background with the Fundamental Theorem of Calculus Part 1. It's helpful but not necessary to know the Fundamental Theorem Part 2. And it's good to know about the finint command on the TI-84 calculator. And we have videos on this channel that address all of those topics, and I will link to them in the video description. So here's a pretty straightforward initial value problem, and we will approach it first from a sort of straight up the gut perspective. So dy dx is x cubed. Let's imagine that y of 1 is 6, and we are asked to determine what is y of 2. So it seems very straightforward to say that if we know the derivative of y, we can find y itself by integrating. And so y of x would be the integral, the indefinite integral of x cubed dx, which is x to the 4th over 4, plus some constant of integration. We should be able to find the value of the constant of integration. So we plug in a 6 for y. We know that when y is 6, x is 1. So 6 is 1 to the 4th over 4 plus a constant. And so c should be 23/4. So we now know what y is. Y of x is x to the 4th over 4 plus 23/4. And so y of 2 is, let's see, 16/4 plus 23/4 ought to be 39/4, which is 9.75. Not terrible, right? It's an easy integrand, and so it was not so tough to approach this in this fashion. But I want to show you an alternative approach that could be even easier. So our initial value problem was dy dx equal to x cubed, y of 1 equal to 6. What is y of 2? And we're going to approach it by means of the fundamental theorem of calculus. And that approach goes like this. If I integrate x cubed from 1 to 2, and those limits are not accidental. One is the value of x for which we know a value of y, and the other is the value of x for which we're attempting to find a value of y. If we were to evaluate this definite integral, we would take the antiderivative of x cubed, which is y, and using Fundamental Theorem Part 1, we would take y of 2 minus y of 1. If we employ a little algebra 1, this tells us that y of 2 is y of 1 plus the integral 1 to 2 of x cubed dx. And you might at this point say, well, so what? I still have to integrate the x cubed. It's a little bit different look, but what does it really buy me? And an answer to what it really buys us is the ability, if it's available to us, to use a calculator to approximate the definite integral without having to do the antiderivative. So this is 6 plus integral 1 to 2 of x cubed dx. And I'm just going to grab my calculator and see what that looks like. So, and the light's not so great. So we said it was 6 plus the integral, and there's a command finint. That's math 9. Our integrand is x cubed, comma x, comma 1, comma 2, and out comes 9.75, which is the result we got using the previous method. In this case, it was sort of a different look, right? It's probably only a slight benefit in terms of the effort we had to expend. But as the numbers get uglier, as the functions get more complex, this workaround becomes a more useful thing to be able to employ. And when your integrand reaches the level of complexity that is beyond your ability to anti-differentiate at the current state of your skills, then it really becomes the only access that you have to an answer in some of these cases. Let's take a look at how this plays out generically. Suppose we have a function y, and its derivative is given by f of x. And let's suppose that f is continuous, so the fundamental theorem is in play. And let's suppose that y of x naught is equal to y naught. So we have sort of generic coordinates for one point, and we know what the derivative is. Then if we were to integrate from x naught to any other x on this interval over which we're assuming f is continuous, fundamental theorem part 1 says that should be the antiderivative of f evaluated at x minus the antiderivative of f evaluated at x naught. In other words, y of x minus y of x naught. And so y of x by algebra 1 is y of x naught, which is y naught, plus integral x naught to x of f of t dt. And we just use the t in order to not confuse ourselves, since x is already in use in another fashion in this integral. I'll flash the formal result on the screen, but it basically says the thing that we just wrote here. Here's an application of this idea that is similar in spirit to a number of problems one might see on an AP exam. And it goes like this. Let's imagine we have a rain barrel with an open top, and it contains initially 5 cubic feet of water. And it begins to rain at a rate r of t equals 1/4 sine of 3t over 8 in cubic feet per hour. I know, humor me on that one. So if the rain falls for 8 hours, how much water is in the barrel at the end of that interval? So if we render this in terms of an initial value problem, it becomes, let's give the rain a name. Let's say W of t for water is the amount of water in the barrel in cubic feet at time t. Then W prime is going to be this function r, right? So W prime equals r, which equals 1/4 sine of 3t over 8. And we know that the amount of water at time 0 is 5. We want to know the amount of water at time 8. Well, using this little relationship we just have been discussing, we should be able to say that the amount of water at time 8 is the amount of water at time 0 plus the change in the amount of water from time 0 to time 5. And that should be the integral for, time 8. That should be the integral from 0 to 8 of this function here. Now, you could anti-differentiate this by hand if you know substitution, or if you are good at sort of wrangling the chain rule in your head. But in fact, there's no need for that, because we have the ability to, that's a little better. We have the ability to just pound this out on a calculator. So this is 5 plus, again, that's math 9, the function int, integral approximator, definite integral approximator. And this is 1/4, which I'll call 0.25, sine of 3, I'll just call it x over 8. Oops, yes, x from 0 to 8. And there we are, about 6.327. Can you tell I teach AP? Cubic feet. So that was not so tough. You just have to know this, how this little thing works. We probably have made our point sufficiently, but if you're willing to sit through one more example, you're welcome to do so. And let's make this a motion one. Let's say we have a particle undergoing rectilinear motion, and its velocity at time t is given by v of t equals t sine t. Its position at time 2 is 6, and we want to know its position at time 5. So essentially, the textbook I use with my students calls position s typically. So we have some function s of t, and s prime of t is the velocity, which is, as we said a moment ago, t sine t. We know that s at time 2 is 6. We want to know what is s at time 5. Well, according to what we've been saying, it should work something like this. The position at time 5 should be the position at time 2, which is 6, plus how much the position has changed from time 2 to time 5. And that is the integral from 2 to 5 of the velocity. And we are once again at a moment where the calculator can step in and do the grunt work for us. So we have, there we go. We have 6 plus finint x sine x, x from 2 to 5, and that is about 1.881. There you go. If you have a little additional experience with rectilinear motion problems, you know that the integral of the velocity function on a given interval of time is the displacement over that interval. So we're just basically asking ourselves, if I start at 6, I move such and such a distance, where do I end up? Hope this has been helpful. Those of you who are students in AP classes, this comes up a ton on the exam. This is really, really something that you want to get comfortable with so that you can deploy it as needed or as desired. Happy mathing.